Zoom meeting. That's all. So just a quick question. Would you guys prefer me to keep the screen vertically or horizontally? So this is horizontal. This is vertical.
Horizontal is bigger.
Vertical is good?
I like vertical.
Okay.
Horizontal gives you a broader spread though.
Yeah, horizontal gives me a broader screen.
Yeah.
What I'm going to do is wait, don't do nothing. We're good. I can hear them through here. We're fine. Okay. So if I need to solve a problem, I will just kindly rotate it horizontally, and then I'm sorry, I'll rotate it back horizontally so that way I have enough room on my iPad screen to write out the solutions. Let's see here. And then I'll re-rotate it back vertically so that way you can see what I did in the previous problem. So I'll go back and forth between the viewing. All right, so let me just rotate it horizontally for now, and then I go back to vertical. So, yes, welcome to Math 132 Review Session 1B, presented by the Mathematics and Statistics Student Success Center. We call it in short MS3. So on Wednesday, was it Wednesday or Thursday? I think it was Thursday. Thursday, right? Yep, on Thursday. Wednesday. Yeah, it was on a Wednesday, my bad. On Wednesday, I did the first review session. It's recorded, and you can find it on our webpage, under MS3's Center's webpage. If you guys want, I can repost that, not the exact video, the recording in the chat, but I can send you the web link for our center. And if you go to our archives, you will definitely see it there. This review session is also being recorded, and I will have the recordings of this session also on our webpage later today. Okay, so here are the directions to our here are our directions of our review session. The purpose of review session number 1 is to prepare students for their upcoming examination, exam 1, students that are essentially enrolled in Math 132, of course. During review session number 1, we will discuss and explain how to solve problems in the following topic, and the following topics summarized in the table to the right. So there are 3 main topic areas: introductory to statistics. I will be taking attendance. Zoom automatically takes the attendance for me, and it tells us how long you're basically in the meeting. So Zoom does that part automatically. The in-person, I would have asked you just to sign a sheet. On Zoom, it's automatic. Excuse me. Yep, you're welcome. So the topics here are introductory to statistics, descriptive statistics, and probability. Those are your 3 main focus areas. Now, depending on your instructor, you may have all 3 of these topics there on your first exam. It could possibly be on your second exam, but there are problems here that, again, you will most likely re-see again on the final. So it's going to be a lot of information, but we will get through it. The breakdown for each topic are shown to the right in purple. So we'll do statistical and critical thinking, types of data, and collecting sample data. The second part is all of the descriptive statistics, namely chapters 2 and 3 of our textbook. So we do from frequency distributions, histograms, scatter plots, correlation, regression, mean, median, mode, mid-range, range, variance, standard deviation, range rule of thumb, empirical rule, and 5-number summary, and the box plots. I think something that I forgot to mention there was z-scores. We have an example of how to compute z-scores as well. For probability, we're going to look at basic concepts. and all of the other formulas that are used, namely to compute the probability of A or B, the probability of A and B. Those are the addition and multiplication rules. We have the complement rule, which means in quotes, not A, and conditional probability. Okay, so let's get started. So problem number 1 states, determine whether the study is an experiment or observational study, and then determine a major problem with it. So part A states that a questionnaire is sent to 10,000 persons or 10,000 people. 5,000 respondents responded to the questionnaire. 4,500 of the respondents say that they love chocolate ice cream. We conclude that 90% of people love chocolate ice cream. And what is wrong with this survey? So what do you think? Is this going to be an experiment or an observational study? Let me know in the chat, or you can kindly unmute your mic if you want to provide an answer.
On a study?
Yes, it's an observational study. How do we know that it's an observational study? Yeah, you're right, Alexandra. Nobody's getting a treatment. In other words, for the definition of observational study, we're applying it here. Researchers do not attempt to modify the individuals.
Question.
Go ahead.
Will we get a printout of this?
No, unfortunately, no. But during the recordings, I guess you can take pictures if you like. You're cool. That's cool with me. I'm sorry about that. Okay, so problem number 1, we also have to determine a major problem with the study. So what is one major problem based off of what we've read from part A? Yeah, Tatiana, the study is bias. That's correct. Why in particular is it bias? That's right. It was sent out to 10,000 people, but how many responded?
Only 5,000.
Only 5,000. Well, careful. Only 5,000. 5,000 of the individuals, they responded, but out of the 5,000, 4,500 of them said they love chocolate ice cream. What makes this somewhat biased is that not everyone answered the questionnaire, right? Only half of the people responded. So this was a case of what we call voluntary response sampling, right? So what's wrong with the study? It's a voluntary response sampling. The again, with voluntary response sampling, there's always a high chance of getting biased results. All right. So that's part A. We took care of that one. Let's look at part B. So in part B, it states that a researcher wants to conduct a study to determine the effectiveness of new golf ball. They got 50 players with different playing abilities and compared their individual scores. They conclude that the new ball is more effective. So, what type of study is this going to be?
This is like an experiment.
Yes, it's going to be an experimental study. In the case of the experimental study, the researcher is applying a treatment to some individuals, and the remaining individuals are technically placed in a control group, right? So, an experimental study, you have two groups. You have the treatment, and you have a control group. Some of the individuals go into the treatment. Some of the individuals go into the control. Well, what's one major problem here? What seems off with the experimental study that was conducted in 1B? I'll give you a hint. Look at the two groups that I have written down. We have a treatment and we have a control. What is the treatment group?
Is
Or-
it the 50 players?
Well, that's the who. The 50 players are getting the treatment. That's right. So we have that the treatment is the 50 players trying out the new golf ball. Based on part B, that's right. They don't have a control. You guys got it. Sorry, I just saw the chat. So the issue here is that there is no control group. If the treatment is the 50 players trying out the new golf ball, what would have technically been our control group? Hey, Raphael, you think you can get that to stop spinning? Yeah, it spins at you. But anyways, yes. Technically speaking, if there was a control group, what would the control group be? If you could just have it to face at least one of the screen or me, that'd be fun. Just don't mess up the mic. So we good? Yeah, that'll be fine. Yeah, because every time you were walking by, it was just rotated that way. Anybody? If the treatment is 50 players trying out the new golf ball, then what would have technically been the control group?
The effects of the new golf balls?
Say it again.
The effect of the new golf balls?
Not quite. Given a different golf ball. That's right, Rachel. Basically, for your control group, if you're trying to really test out the effectiveness of the new golf ball, then try out different golf balls or the old ones. Right? So technically, it should be those using old golf balls. And those are your solutions, right? 1A was observational. Again, in observational study, the research do not attempt to modify the individuals of the study. And the major problem was that it was a voluntary response sampling. which results in that there's a high chance of getting biased results. Part B was experimental study, because we know that in an experimental study, the individuals are split into two groups. You have treatment and control. Researchers are applying a treatment to some individuals. The remaining individuals are in that control group. So the treatment, for this example, would have been trying out the new golf balls, whereas on the other hand, the control group is those using the old golf balls. Or the 50 players, rather, should have been also in that control group where they're using that old golf ball. So that way they have some compare and contrast, right? Here, it doesn't say that they were comparing and contrasting the new golf ball to the old golf ball. Instead, they were just comparing their individual scores, right? Like, who's better, Michael Jordan or LeBron, you know? It's like one of those cases in part B. Yep, that's what it was. All right, so any questions with problem one? Is it okay for us to move on? All right, so I'll rotate the screen now. So that way, I don't know how well you guys will see it on your end, but I'll try to keep it in this format. Will this be good for you, Martha? Will you be able to see from up there? I know, because it's like the higher one. Okay, cool. All right, so let's look at problem number 2. Problem number 2 states that for the following study, identify the population, sample, the statistics, and the parameter. Okay, so the population is, by its definition, everyone of interest, whether that could have been humans, animals, or even possibly objects, right? So it's all individuals of interest. It's just a little harder for me to write like this. So that's our population. The sample is always a subset of the population. So I abbreviate population as POP. I could zoom in. The thing is, when I zoom in, it's better for me to rotate it horizontally. That's why. Let me just get through problem number 2, and then we'll sort of have a vote on this. All right. The next one is the word statistic. So statistics is a numerical measurement. It's data that we gather from what? From the sample or the population?
The sample.
The sample, right? If you look at the word statistics, it begins with the letter S, and sample begins with the letter S, right? So a way to distinguish between statistics and parameter, even though they have almost the same definitions, the statistics is associated to the sample, or it corresponds with the or comes from the sample, and the parameter is for population. Here's a little picture to go by. So first, you start off with your population, right? After you figure out what's your statistical study all about, like your questioning and all that good stuff. After you have your population, you want to create a, because some population, of course, is just so large, you want to get a good representative of it. So you choose a sample. Then from your sample, you gather sample statistics, right? Or just statistics for short. Right? You collect, you gather, you collect, or sorry about that. Or you organize your information. From your statistics, you can run what we call, and you'll see this towards the ending of the semester, you'll run what we call inferential statistics to get your parameters. And the parameters are what's being used to make some sort of general conclusion regarding the population. All right, so this is a little flow chart, should help out. So let's figure out part B now. So part B states, problem 2. It states that a university wants to determine the average mean amount of money first-year college students spends on school supplies for their courses. Excuse me. Out of the 125 randomly selected students surveyed, it was found that the average spending of these students were approximately $1,200 per year. So, what is our population for this study? Who are the individuals of interest?
A university.
Say it again.
A university. University.
Unfortunately, no. The university is actually the one conducting the research. And, excuse me, we're just trying to figure out the population. Who are the people of interest?
The first year
The
college
people being
students.
surveyed.
That's right. It's the first year college students that attends the university, right? Whatever university that is. So we say population is all. One of the key words, by the way, is that when you're talking about the population or describing it, at least, you should use the word all. So it's all college students. First year college students. That attends the university. Okay, so we got our population down. Can we now identify the sample?
Yes.
Yes, we can. What is our sample, Melissa?
125.
Correct, but you have to just elaborate a little bit, right? You just can't say 125, right? It's like-
The random student selected.
That's right. So what we're going to say is that our sample is the 125 randomly selected first year students. Okay, now from the sample, what information did we obtain regarding the sample? Or what information did the university obtain?
They got the average of 1,200 per year.
Yeah, the average spending for these students were approximately 1,200 per year. So is that a statistic or a parameter? That would be your statistics. That's right, Tatiana. So our statistics, is going to be the what information we got. So we got the average spending. So we say that the average spending of our sample is $1,200 or approximately $1,200 per year. What about the parameter? Were we given any numerical value regarding the population here? For example, no, it doesn't. But we can generalize, right? For example, the statistics, again, just going back to my chart, the little visual I have, when we're going to go into the ending of this introductory to statistics course, you're going to learn about inferential statistics. And you're going to use information regarding a sample to determine some numerical value for a population, right? sometimes you have to create something called, we call it a confidence interval. Sometimes you have to do a little bit of hypothesis testing. You'll see that later down the road. For now, we could just make a general statement regarding the parameter. We say the parameter is the average spending of all first-year students that attends the university. Right. So again, we don't have a numerical and a precise numerical value for the parameter. But again, later down the road in this course, you will. You definitely will find something to make a general statement regarding this parameter. Any questions here with problem 2? Okay. So I know somebody asked me to zoom in earlier. The thing is that zooming in could be quite could be a little bit difficult on my end, because I could zoom in, like, let's just say going to showing the solution rather. I usually do that. So this is like the pros and cons I have with my screen sharing, is that the vertical is good because you can always see what I did in problem 1, but then it gives us a tiny view of everything. On the other hand, when I do the horizontal view, yeah, I'm so sorry about that. Yep. When I do the horizontal view, you get a much better view, but then you just gotta make sure you stay on top of the previous problem, because I gotta keep going on. No, no. These are slides that I created. This is better? Okay. So I'm going to stick with this view, because again, you get to see the full-blown screen. It's just that you won't be able to see the previous problem. I think if we were all in person, it would have worked better, but it's okay. All right, so let's continue. So problem number 3 requires us to classify each variable as discrete, continuous, or neither, then explain why. So part A states the number of minutes in an hour. Is that going to be discrete, continuous, or neither? It is discrete, Martha, you're right. Why is it discrete? What's the key phrase there? That tells us that 1A is discrete. It's okay, you can go back. Explain what they are first. Well, no. I'm not going to explain it first, because then it gives away the answers. Hence the questions say, explain why at the end.
Is it the number of minutes in an hour?
Well, it's just, well, you read the whole phrase, just a part of it. What part of the phrase tells us that it's discrete?
In an hour?
Not the an hour,
Mm.
the number, right?
Oh,
Look, if you guys have your notes, excuse me, my bad. I had coffee earlier and I had some breakfast and it's like still stuck in my throat somewhere. But the number of minutes an hour, this is discrete, and you have to use the definition of what it means for a variable to be discrete. So I just can't explain it right away, because it gives away the answer, right? Instead, you have to, provide me with an explanation. That's why we're here in this workshop.
It's something that can be countable. That's what my professor
right.
told me.
Yeah, there you go. It's something that is countable, right? The data values here. Well, can you count how many minutes are in an hour? Or what is the total number of minutes in 1 hour? Yeah, how many minutes are in an hour? 60 minutes. You can actually count those number of minutes. So it's discrete because of the fact that data can take on specific values. And if data can take on, can only take on specific value. Sorry, I write the word only first. Can only take. That's what I wanted to say. Then it's countable. Okay, let's look at part B now. Now this one gets, the way that it's phrased is, it makes it tricky now. Part B states the amount of time spent sleeping. Is this going to be discrete, continuous, or neither?
Continuous.
This time, although our variable is talking about time, here we're dealing with continuous data set. And why do you say it's continuous? Can you apply the definition to explain your answer?
Because it's an infinite number of possible values.
That's right. So here we say that it's continuous because the data can take on any value in an interval. When you're dealing with a continuous data set, yeah, that one is tricky. When you're dealing with a continuous data set, the data values are uncountable, or you're dealing with some sort of scaling or some sort of measurement, right? So these are three words that you can associate continuous with, right? So just like how I had discrete, where I underlined the word number, that was like a dead giveaway. But for continuous data sets, again, it will be uncountable. Think of a scale, or you can think of a measurement, right? Here's another example for continuous data sets. Look at this this number line. Let's say that my number line starts at 0, right? So it's more like a line segment. I'm starting at 0 and I'm ending at 1. There's an infinite number of values that goes after the number 0, that comes before 1, right? For example, what's one number that you can choose that's between that's within this interval from 0 to 1? Can I get a value? That's between 0 and 1.
0.5.
Yeah, 0.5. Now, what value would you like to say that comes after 0.5?
0.75.
0.75. Okay. So now between that 0.5 and 75, I can say that you're wrong. I can say that there's another number that comes before 0.75 that is after the 0.5, right? I can argue that that value can be 0.6. Let's say 0.6 was somewhere here. But then I'm also wrong. Because if you look at the interval between 0.5 to 0.6, is there a value that comes after 0.5, but yet less than 0.6?
Yes.
Yeah, what value can you think of?
0.55.
Yeah, 0.55, right? Just keep cutting that in half. Essentially, when you're going to keep applying this, you're going to find out that there are infinitely many values that's in this little range of 0.5, let's say, to 0.6, right? There's essentially no next value, right? You could have argued that it's 0.55, but then somebody could turn around and say, no, it should be 0.54. And then it just keeps going on and on and on and on, right? It's uncountable. So anytime you're dealing with something of a scale or a measurement, it's continuous. Think about when you jump on a scale, right? Let's say like we were jumping on a scale. I can't really draw the feet well. Let's say that's my feet. I have like a SpongeBob square feet, like, but let's say that's my feet on the scale, and then the scale does the reading, right? It gives you your number. When you jump on that scale, do you ever see that number always jumps back and forth, the decimal point? Like you could be like 154.5, but then that 0.5 will jump to like 0.43 or 0.6, 0.7. Well, that's a classic example of continuous data set. You can't really count your weight. When you jump on the scale to measure it, on the scale, it jumps back and forth. And then, if you lean in one direction or the other, or you're putting a little bit more force on one of the feet, then yeah. So scales are, weights, they're good examples of that. All right. And part C states, okay, well, we have academic rank, professor, associate professor, etc. Is it discrete or continuous?
Discrete.
Neither.
It's neither. If it had the number of academic professors, right? So academic rank, I'm just going to write it that this result here is going to be neither, because what we're dealing with here is not quantitative data. We're dealing with qualitative data. And with qualitative data, we know that we're looking at attributes, labels, or categories. When I say attributes, I'm more or less talking about the qualities. You have labels and categories. So the academic rank, those are categories, right? Professor, associate professor, assistant professor, lecturers, adjuncts, etc. If I were to say, right, so let's do a part D. Let's say if I wrote the number of academic professors at a college, then this one would have been discrete, because I used the phrase the number, right? We can actually count, no matter what college it is, we can actually count how many professors are working at that college, or employees of that college. So we see the difference between part C and D. Part C, it just said academic rank, so that implies that we're dealing with qualitative data. Now, if it were talking about the number of academic professors at the college, that's discrete because we can count them. Sounds good?
Yeah.
Yeah.
Do we have any other questions? Okay, so I'm going to move on to problem 4. I'll probably give it a minute first. I'll give you a minute for anyone that's just want to take a quick picture. And then I'll do problem 4.
Wait, so qualitative data can be continuous or discrete?
That's right. That's
Okay,
right.
okay.
Quantitative data could be discrete or continuous. Yep. But qualitative, on the other hand, is specifically attributes, labels, or categories. Or quantitative, you can either count it or measure it. Okay. So let's go on to the problem number 4 now. So problem number 4 states determine which of the 4 levels of measurement, nominal, ordinal, interval, or ratio is most appropriate for the data below. And I gave you some hints. I gave you the definitions to use it to help you solve this the 4 parts. So let's look at part A. Part A, or actually let's do it this way. Let's say that we go through each of these definitions and then we try to figure out which one is part A, B, C, and D. So starting with the first definition I have nominal. So the nominal level of measurement is characterized by data that consist of names, labels, or categories. Nominal data lacks any ordering or numerical significance. So data at this level, is it quantitative or qualitative?
Qualitative?
Qualitative.
Yeah, it's definitely qualitative. So looking at parts A through D, which one of those data is qualitative? We have total annual wages for first-year college students, the top 10 the NBA players of all time, the number on a
B and C.
baseball player's jersey, or the temperature in degrees Fahrenheit. That's right. So most of you did say part B. You're correct on that. But we need to figure out the most appropriate for the data below, right? So part B is nominal, don't get me wrong, but there is a higher level of measurement that we use to classify part B. And I'm going to show you the difference with the next one of these definitions. But there's also just one particular data here that is strictly on the nominal level. And Tatiana mentioned the other one. It was the number on a baseball jersey. When you think about a baseball player, or let's just say think about the number 2 in the bronze here with the Yankees, who comes to mind when you think about the number 2? Yeah, you think about Derek Jeter, right? So the number on a baseball player is definitely qualitative because it describes that baseball player. It gives basically that the player's identity. So this is strictly at the nominal level. Okay, let's look at our second definition. The second definition states that data are at the ordinal level of measurement if they can be arranged in some order or some rank. Data at this level are typically descriptive, meaning it's qualitative. So the other qualitative data that you guys did mention in this in the answer choices here were part B. But part B doesn't just go up to the nominal level. It also goes up, in fact, it actually goes all the way up to the ordinal level. And the key distinguish there as to why it's going all the way up to the ordinal is, well, look at the key phrase there in answer choice B. Or question part, or part B, I'm sorry. What does part B say about these NBA players of all time? Who are we looking at? Yes, it's a rank. Namely the top 10, right? So the top 10 is another way of phrasing that we're ranking 10 basketball players of all time, right? From high to low. So this is going to be ordinal. All right. So now let's look at the interval and then the ratio levels. So data are at the interval level of measurement if they can be arranged in some order right? You could put some sort of ordering onto your values, and differences between the values can be found and are meaningful. Data at this level do not have a natural zero starting point at which none of the quantity is being presented, right? So one of the key difference between interval and ratio is that in an interval, there's no natural zero starting point, whereas at ratio level, data at that level can be arranged in some order, difference can be found and meaningful, and there is a natural zero starting point. So look at choice A and choice D. Which one of these choices does not have the natural zero starting point? Yes, temperature, right? If you think about it, when we say 0 degrees, is 0 degrees a starting point for a thermometer or when you're reading temperature? Well, let me clarify that. So when you look at no, the answer would be no. 0 degrees is not your starting point, because we know that if you go all the way up into Canada or Alaska or even Antarctica in the next couple of months, you're going to be a negative. Well, I think over there they do Celsius, but you can convert it to Fahrenheit. We can convert it to Fahrenheit, depending on how bad their winter is, and if there's no if global warming is coming into play and they're like in the 20s, 30s, then yeah, there's no natural starting point there with 0 degrees. So data at this level is going to be at the interval level, right? So 0 degrees Fahrenheit is not a natural zero starting point. It just means that if it's 0 degrees, it's too damn cold, and I'm hibernating. Okay, so that leaves us with part A. Part A is going to be now the ratio. The key difference between ratio and interval is that in the ratio interval, the ratio level of measurement, you do have that natural zero starting point. So if we're talking about annual wages, what does that $0 imply? Is the first year college student employed? No, right? So here it's ratio. We do have a natural starting zero starting point. That $0 implies that student isn't working. All right, any questions to problem 4? I think we got through most of the definitions that I wanted to go through. That's all of probably chapter 1 that I wanted to do. Now we can go into chapter 2.
Quick question. Is ordinal like the grading scale?
That's right. Ordinal is like the grading scale. Like if you're looking at the letter grades that you can receive in a course, then yes. Okay, we're going to continue. I don't think this one was too bad. So in problem number 5, we're going to have to do a lot of things here. This problem, if your class, by the way, uses Pearson MyLab, you will definitely see a question like this on Pearson. So it states the number of individuals is equal. Sorry, my bad. I was reading off of my my solution set to my other thing by mistake. My bad. Problem 5. Identify the lower class limits, upper class limits, class width, class midpoint, and class boundaries for the given frequency distribution. Also identify the number of individuals included in the summary. Okay, so when you have a frequency distribution table, your first column, right, where it talks about the daily commute times in New York City, those are essentially your classes. So those daily commute times, I think that's supposed to be in minutes. Or the values that you see in that column are given in minutes. You can see that those values were bin or grouped together, right? So you have the first class from 0 to 14, all the way down to the last class of 90 to 104 minutes. To the right, you have the frequency. The frequency is the number of data values that falls within that class. So for example, if you look at the 30 to 44 class, we have that 17 people reported that that's their daily commute time in New York City. Okay, so we have to first figure out the lower class limits and the upper class limits. What are your lower class limits? Can we list? Say it
Is
again.
it
0 to 14.
Unfortunately, no, it's not going to be 0 through 14.
is
That's
it
the-
0,
Gonna be 0.
0, 15, 30, 45, 60, 75, 90?
That's right. It's basically all the first numbers that you see in each class, right? So it's gonna be the 0, 15, 30, 45, 60, 75, and 90. That's all your lower class limits. Well, if those are going to be our lower class limits, what is the upper class limit?
14, 29, 44, 59, 74, 89, and 104.
That's right. Very good. This will be 89. Oops. 89 followed by 104. So we have the lower class limits. We have our upper class limits. Now what we need to do is take care of the class width. Anybody know how we can find the class width?
Isn't it subtracting the upper and a lower?
You add them,
Careful.
right? And then
No.
you divide it by 2.
No. That would be another formula. That would be for class
Oh.
width.
Oh,
So-
yeah.
And then
Subtract the 15 and the 0, and then 45 and 30, and then 75 and 60, and then 90 and 75.
What are we doing with those numbers again? I'm so sorry. You said what?
Subtracting.
That's right. You don't have to do it for all of them. You just got to do it for any consecutive lower class limits. Right? So let me just write the definition down so that way we have it. So I'm just going to slide down a bit. So we're going to say that the class width, the way that we compute it is that we take the difference between any two lower class or any two consecutive lower class limits. Okay, so you can take the first two class, for example. If you take the difference between the 0 and 15, what would that be? Yeah, it would be 15.
15.
All right. You don't have to use that one. You could also use somewhere in the middle. You could edit the difference between 45 and 60, right? What is 60 minus 45?
15.
It's still 15. That's right. So you can use any two lower class limit. So what we have here for this problem is that the class width is going to be 15. Right? Just apply the definition. Take the difference between any two consecutive lower class limits. All right, so we took care of that. now we can take care of class midpoints. So somebody mentioned the formula earlier. Class midpoints is when you take the sum of the lower class limit and the upper class limit, you add those two values together, and then divide it by 2 for each class, right? So what I'm going to do is I'm going to extend my table out a bit. I'm going to call this midpoint. And because we're going to see this again, this is just a mathematical notation. When we're looking at midpoint, we just denote it as an X with a subscript M, okay? And what it tells us that we're going to do again is just take the upper class limit, add it to the lower class limit, then divide by 2. So what is 0 plus 14?
14.
14. So you're going to take 14 and then divide it by 2. So what's 14 divided by 2?
Seven.
It'll be 7. If it's related to sorry, I just read a message in the chat. Hey Laura, if it's related to what we're doing, then you could ask, but it has to be based on somewhat of the problem. Like if you ask me something else, I might not be able to answer it. Not at the moment. You're welcome. Okay, so we got the first class midpoint. Let's try to get the second one. The second class midpoint is going to be, well, 15 plus 29 divided by 2. So what's 15 plus 29? 44. And then you'll take 44 divided by 2. So what's 44 divided by 2?
2.
22.
22. Okay, let's look at the third, in our third class. We have 30 plus 44 divided by 2. So 30 plus 44 should be, I think, 74. And then we're dividing 74 by 2. So what's 74 divided by 2?
37.
37. That's right. If you look at these first 3 classes, we got their class midpoints. Do you see a pattern with these values? For example, notice that we started with the number 7, then we got 22, then we got 37. Is there
15.
a pattern that we see? Say it again.
15.
You're right, Genesis. We're going up by 15s. And if you notice, where did we see the number 15 before?
Our class width.
Our class width. That's right. So if you find a couple of class midpoints and you see that the pattern is that it's going up by exactly what your class width is, then you can use that pattern to fill out the rest of the table, right? For example, what do you think would be our fourth class midpoint?
52.
52, right? 37 plus 15. For our next class, 67. The sixth class, 82. And the last, 97. Okay, so on my lab, unfortunately, they're not just going to accept your table as well, right? Remember, I told you this problem came from my lab. So you actually had to write out your class midpoints. So you list them. You say class midpoint, and then you list the values in order. So those values were 7, 22, 37. We found the first 3 manually. And then we found that the pattern was that it was going up by 15s, which is exactly your class width. So the remaining numbers were 52, 67, 82, and then lastly, 97. Okay, any questions? Just 2 more things for us to do here. Right, so I have the class midpoints already listed above. So all I'm going to do is just scroll back up real quick so I can finish off my table. You see, we've got 2 things left to do. Those are to get the class boundaries and then identify the number of individuals in your data set. Okay, so here's the class boundaries. Basically, if you look at your classes, the class boundaries is used to fill in the gap. And if you want to fill in your gap, you take your lower class limits, which we already identified, and we will have to subtract by 0.5. To figure out the upper class boundaries, you add 0.5 to the upper class limit for every single class. So let me just write out these two general rules that we do, and then we'll fill out the table, right? So for lower class limit, lower class boundary, we are going to subtract 0.5. Again, we're subtracting 0.5 from the lower class limits. For the upper class limits, or the upper class boundary, we add 0.5 to the upper class limits. So look at your first class. If your first class is from 0 to 14, then what do you think would be your lower class boundary for the first class? In other words, subtract 0.5 to the first lower class limit. What would it be?
Negative 0.5.
So it'll be negative 0.5. Now, on the other hand, for the upper class boundaries, you have to add 0.5 to those upper class limits. So 14 plus 0.5 is going to be what?
14.5.
14.5. And now we continue this. Look at your second class. From 15 to 29, you would have to subtract by 0.5 get your lower class boundary. Upper class boundary, add 0.5. So what would that the class boundaries be for the second class?
14.5.
14.5, yes. And for the upper class boundaries?
29.5.
29.5. Okay. Can I get a volunteer to tell me what the third class boundary is going to be?
29.5 and 44.5.
29.5 to 44.5. The next one?
44.5 and 59.5.
Continue.
59.5 and 74.5. 74.5 and 89.5.
Yep. And the last one?
89.5 and 104.5.
Yep. That's right. So do we see that the class boundaries, some of them are repeating?
Yep.
Yeah. Like, for example, look at the first class. The upper class limit was 14.5. And in our second class, the lower class limit was also 14.5. So essentially, again, class boundaries is what you use to bridge the gap. So that's one way of checking that your solution is valid, is that there's this overlap. There are these particular repetitive values that are bridging the gap in your frequency distribution. So if you want to list on MyLab, by the way, all the class boundaries in order, you would have essentially worked with all of the lower class boundaries, right? You'd have took all the negative 0.5, 14.5, all the way down to 89.5. And then you would have included the very last upper class boundary. So those values are going to be the following, right? So class boundaries. And I'm not saying lower class or upper class, this is just general. In order would be negative 0.5, 14.5, 29.5, 44.5, sorry, 59.5, 74.5, 89.5, and then lastly 104.5. Okay, so those are the class boundaries. The last thing now is to figure out the number of individuals in this data set. So I'm just going to write the formula down here below. We say that the number of individuals is equal to your total frequency. And mathematically, we use the sigma notation, the Greek letter, sigma, to represent the sum. So we're taking the sum of all of the frequency for each class. So just quickly, looking at the frequency column, if you were to add up the values 3, 9, 17, 35, 18, 9, and 2, you would have got your sum of F. So I actually have to add it up myself as well. Just double check. But yeah, if you add it up, what do you get? Careful, Rachel.
93.
It's 93. You can't say negative 93 or mark it wrong. So when you add it all up, we're going to get 93. Oops. All right. Is there any questions to problem number 5? I'm just leaving it this way because again, I had to use two slides to get through the whole thing. So on my lab, what I have on the second slide is basically all the data values or all the numbers that you have entered. I just used that table there, or I extended the table so that way I could have showed you how to as a demonstration how to get the midpoint and class boundary. Okay, let's look at problem number 6. Problem number 6 states that we want to use the frequency distribution from the problem set from problem number 5 to construct a histogram. Then comment on the distribution. Is it approximately normal, skewed left, or skewed right? So when you want to construct a histogram, the first thing that you do is you begin with a pair of axes. So you have one that goes vertically. Sorry, I forgot to hit draw. So we have one pair, one set of the axis that's going vertically, and the other one is going horizontally. The one that's going vertically, where I just include this little line here, the squiggly line, what typically goes there? The classes or your frequency?
Frequency.
Yeah. So on the vertical axis, we have our frequency. On the other hand, the horizontal axis, we have our classes. All right, so I'll show you how I fill in the frequency distribution table. Sorry, how I complete the histogram. Your instructor might show you a little bit differently, but we will still get the same overall shape. First, I look at my frequency, right? I look at my frequency and then I sort of come up with a scaling. So for me, I can't fit, if I go up by ones, I can't fit the number 0 all the way up to 35, given that 35 was the max. So I got to figure out an appropriate scaling for this. So anybody have any way that they want me to scale, prefer way that they want me to scale the frequency axis?
By 5s.
You can go up by 3s. 3s work. But you can also go up by 5s. I think I could go up by 3s. I think 3s I could fit it all. Let's see. So 0 is where both of the axes meet. And now I'm going up by 3s. So let's see. Here's 3, here's 6, here's 9, here's 12. Probably can't. here's 15, here's 18, say here's 21, 24. Let me just fix this part. Let's say here's 27, 30. I probably can't fit it for real. 33, 36. All right, so that's my scaling. I should have wrote 21, 20, the 18 to 24. I should have wrote them smaller. But yeah, but anyways, it worked. Fives would have been a little bit more convenient. I would have had the numbers a little spaced out more nicely. That's okay. Now I need to scale my my horizontal axis. The thing is that for me personally, I don't like writing out the entire class 0 through 14 and then 15 through 29. So what I do is I just use the first lower class limits, or sorry, I just use all the lower class limits. So the first one was already presented to us. It was 0. So for my second class, it will begin at the number 15. For my third class, it begins at the number 30. For my fourth class, it begins at 45. For my fifth class, it begins at 60, just making sure my numbers are right. Yep. My seventh class is at 75. And my last class would be starting at 90. So I just list out all the values for the classes, basically the lower class limits of all the classes. Okay, and now we draw the bars for each class, where it corresponds to, again, the frequencies. So the first class, 0 through 14, has a frequency of 3. So I'm drawing a bar that has a height of 3, which is shown in red. My second bar, from 15 to 29, has a frequency of 9. The next one has a frequency of 17. Yeah, so that'll be a little bit under the 18 mark. Then the next one, we go all the way up to 35. By the way, when you're drawing a histogram, notice that the bars, there's no gaps, right? The only time you probably have a gap is if you have a frequency of 3, a frequency of 0, where you might see that there's a little gap or space in your histogram, but that would have implied that a class has a frequency of 0. The next one is 18. And let's see, next one is 9. And the last one is 2. Okay, so that's our frequency distribution table now being organized into a histogram. So what do you think? Is the histogram approximately normal, skewed left, or skewed right?
Normal.
Yeah, it's approximately normal. What do we know about approximately normal distributions?
They're even.
Not
Like
quite.
a bell shaped.
It's bell. You see, it's even if all the bars were the same height. That's called uniform distribution, which you might see a little later on. But for now, in this example, it's approximately normal. Right? It resembles a bell-shaped curve. Right? The bell-shaped curves look something like this. Not the best of bells, but a bell nonetheless. Yes. Alrighty. Sounds good?
Yeah.
Okay. I'll keep this up for right now. We'll do problem 7. So problem number 7 says to consider the scatter plot shown to the right, and then which of the following could be the value of R. So look at your scatter plot. What's something that you can observe regarding your scatter plot?
It's negative.
Why is it negative? How can I write that as a phrase as to why it's negative? It's going down. That's right. So one way of phrasing it, that it's going down, it's negative, is saying that as x is increasing, right? Because technically speaking, we read graphs from left to right first. So as x is increasing, what happens to the y values?
Decreases.
Y decreases. Right, that's the relationship we can see between x and y. Is whatever those variables were, as x increases, y is decreasing. Okay, now think about a line, right? Let's say that I just drew a line. Remember, this is a scatter plot, so it's not a perfect line that's going to hit all these points. It only would have hit it if, of course, all the points lie on the line. But let's just say that this is my line, roughly speaking. We have to determine the value of R. And because we have a negative relationship, there are some answer choices that we can automatically get rid of. Right? What answer choices can we automatically get rid of in part A?
0.11, 0.44, 0.969.
That's right, because again, we can see that as x increases, y is decreasing. This is a negative relationship. And with a negative relationship that is linear, then the value of R is not going to be anywhere positive, right? It's never going to be anything greater than 0. So we have two possible choices here, negative 0.969 or negative 0.474. So which one do you think is the most reasonable?
Negative 0.969.
That's right. It will be the negative 0.969. That would be the most reasonable choice here for R. The reason why this one's the most reasonable.
How you got that?
I'll explain it. The reason why this is the most reasonable rather than the other one is that if you look at R is always a value between 0 and 1. So think of this scaling. Let's say that I start with -1 and I end at +1 and 0 smack in the middle. What I know about these relationships is that if you're closer to the -1 or the 1, your relationship is always going to be strong no matter what, right? So as you're getting really close, like my arrow's pointing, as you're getting close to this -1 or even getting close to this +1, you're either going to get a strong negative or a strong positive. If you get anything smack in the middle, closer to 0, we say that's weak or no correlation. Right? So R is just trying to measure our relationship here. Looking at our graph again, you can see that most of those values, although they don't hit the point, those points, they're not hitting the line exactly. They're all relatively close to it. So we're gonna have a strong negative rather than a weak negative or no correlation. Another way of looking at it mathematically is compare those two numbers, negative 0.969 to the negative 0.474. Which one's closer to negative 1? Well, it has to be the negative 0.969.
Got it.
You're welcome. All right. Let's look at part B. So part B, you have to now give, given that the regression line has a slope of 0.493 and a y-intercept of 9.78, find the slope intercept equation of the line. Right, so for part B, we use this formula. So most of you probably seen it from your text. It's y hat equals b1x plus b naught, or b0. This, by the way, is no different from y equals mx plus b, the slope intercept form of the equation of the line. Right, so b1 is what gives you your slope. B naught is the y-intercept. So since both of those values were given to us, we didn't actually have to compute these values, just insert it into your formula. You get that y hat is equal to 0.4, sorry, it shouldn't have been 0.493. I just realized that when I was typing out my slides, that the dash there, the hyphen, that's actually supposed to be a negative sign. So my bad. The slope should actually be negative 0.493 times x plus the y-intercept, which is 9.78. So my apologies regarding part B. The hyphen that I circled there, that's actually a negative sign. And it makes sense that it is a negative sign because what type of relationship that we have regarding this line or the variables? It's a negative one. So the slope of the line was decreasing. Okay. Let's look at part C now. It says that use the regression line to predict the y value of x. So when x is equal to 21, we're solving for y hat. In order for us to solve for y hat, just plug in the value of x. And then if you need to, round to the nearest, or round to 3 decimal places. So you get negative 0.493 times the value of x plus 9.78. So we can work this out one step at a time. You can take the negative number, that's your slope, and multiply it by 21. And then add that value to 9.78. So if you did the multiplication correctly, you should have got something like negative 10.353. And then when you add it to 9.78, what will be your final answer? Yeah, negative 0.573. And that's it. That'll be your final answer. For those of you that are in taking a Math 132 course, I know in person, this is something that you'll definitely see again in the final. This is something that I don't think anybody should get wrong. Okay. All right. I'll see you around, Martha. I'll be here. Yeah, I'll be here. 2:40? Maybe. Yeah. Double check with us. All right, you're welcome. Any other questions?
Excuse me, want to ask the B question. Mx, M, what's the mean by X? By the mean by M?
No, M stands for slope, right? So the B1,
Oh, slope. Okay, thank
yes,
you.
B1 is your slope,
Thank you.
and the B nod, that's your B, that's your y-intercept. So from an algebra course, students usually recognize this formula as y equals mx plus b, the slope-intercept equation of a line.
B is y9, right?
Y-intercept.
Oh, intercept. Thank you.
I abbreviate.
Thank you.
I got a question for me, Warren. It's about part A. Is the answer always going to be the strong negative or the strong positive?
It should be, or if there's a scatter plot that has something where you can't recognize the correlation at all, then it should be something that's close to zero. The closest thing to zero.
Okay.
It really varies. It depends on the scatter plot that you look at. But for these type of problems, it has to be something that you should recognize, you know? Is it strong, weak, or if it's strong negative, weak or no correlation, or strong positive, one of the three. But if it's like a weak or no correlation, it wouldn't really make sense to do a regression line problem. Just a heads up. Okay, let's look at problem 8. So now we're gonna get into more calculation stuff. So I think up to problem 7, problems 5, 6, and 7 were all chapter 2. Now we're heading into chapter 3. So chapter 3 goes from problem 8 all the way, just want to quickly show you, all the way up to problem 14. So chapter 3 is where you look at things like the measures of center, the measure of variation, the measure of relative standing, like such as the 5-number summer. Okay, so problem 8 states listed below are the maximum speeds, kilometers per hour of randomly selected roller coasters in the United States. Find the mean, median, mode, and mid-range. And if necessary, round your final answer to 1 decimal place. So before we begin any calculations here, we have to find the median. When you're finding the median by hand, what is one thing that you have to make sure the data values? What's one thing you got to make sure about the data values?
Order even numbers.
Yeah, you order the numbers. So let's actually put these values in order first because they were not, and then we solve the rest of the problem. So in order, what would be your first value?
45.
45. So I'm going to cross it out from my list. Okay, what's the next value that comes after 45?
57.
57. What comes after the 57?
65.
65. After the 65?
65 again.
Yes, it does. 65 appeared twice, so we have to make sure we rewrite it twice. Okay.
70.
70?
Yeah. 76.
76.
Yeah. 81.
You can continue. You don't have to wait on me.
97. 105. 117. 151. 194.
And okay, cool. All right, so we have all the data values listed in order. Now we can go ahead and find the mean, median, mode, and mid-range. So these are randomly selected roller coasters in the United States. So we know that in terms of like notation-wise, we're dealing with a sample. So the sample mean, we say that it's X bar is equal to the sum of all the data values divided by n. So you would have had to take all the individual data values, add them up, and then on the bottom, you would have counted how many individual values we have. So how many data values do we have? Yes, we have 12. So we just got to figure out what's the top number. Again, the way that you get the top number is you add up all the numbers that are on in our data set. And then we could be able to divide that by 12. Only thing is that on my end, I don't have the solution set yet to the slides. So I have to actually work some of them out, but I got the top number. What is the top number? The sum of all the data values. That's right, Rachel. We have 1,123, and we divide that by 12. Just make sure that you follow the rounding directions. So here we're rounding final answers to 1 decimal place. So when you do 1,123 divided by 12, what do you guys get?
I got 93.58.
Careful. Oh, yes, 93.58. I think somebody entered 93.33. I think you made a mistake. It should be 93.58 in front of all of those threes. Okay, but we're rounding it to 1 decimal place. So what does the 8 tell the 5 to do?
Add 1. It's gonna
Got
be
1.
Yeah, you're gonna go up by 1. So your final answer should be 93 point what?
6.
0.6, yes. 93.6 kilometers per hour. Okay, good. That's your mean. Let's get the median. Anybody remember what's the definition for a median?
Would it just be like the middle value?
Yeah, the median is equal to essentially the middle value, but you got to be careful. I technically call it the halfway point of your data set. In other words, 50% of the data values are less than the median, and the other 50% is going to be greater than the median. In your data set here, since n is equal to 12, Wendy, hello, how you doing? Are you here for my stats review? Okay, cool, just checking. So since the median is the halfway point of your data set, and since n is the number of data values in our data set, remember, n here is an even number. So when you're doing this manually by hand, the median is actually now going to be the sum of the 2 middle values divided by 2. So what are your 2 middle values here?
$76 and $81.
So for this data set, we have to take 76 plus 81 and then divide it by 2. So if I had an odd number of data values, like let's say if hypothetically speaking, the 194 wasn't there, then the median would have just been the direct middle value. It would have been 76. But because we have an even number of data values, you add up the 2 values, then divide by 2. So what's 76 plus 81 divided by 2?
157.
157. 157 divided by 2 is?
78.8.
78, try again.
0.5, I'm sorry.
It's okay. 78.5. All right, so that's our sample mean. We have our median. Let's talk about mode and then mid-range. So what is the mode for this problem?
65.
65. And again, that's just because it appeared the most. And what about the mid-range? Anybody know how to compute mid-range?
Is that the highest value subtracted by the lowest value divided by 2?
Close. You see, the mid-range is a rough estimation of the middle. So you're actually you have to add the low and high values, right? So I'm just gonna say low plus high divided by 2. So what are your low and high values? Well, that was 45 and 194. So you take 45 plus 194 and divide that by 2. What's 45? When you add up 45 and 194 together, you should get something like 239 divided by 2. When you divide it by 2,
119.5.
you get 119.5. So those are your 4 calculations for the measure of center, essentially. The samples, the mean, the median, the mode. Sometimes your data set can have no modes because there's the data values that none of them appeared the most frequent. And then you have the mid-range, which is just a rough estimation of the middle. Okay, questions to problem 8?
No.
Okay, let's continue. So in problem number 9, one other additional problem that they have on my lab regarding the measure of center is figuring out you're trying to figure out the mean for a frequency table. So let me give you the formula first. So here's a case where I can give you the formula first, and then I'll explain how I utilize it. So the formula. Oh, sure. Taking a picture? My bad.
I'm done. You go down.
All right. So the formula for problem number 9 states the following. Your sample mean for a frequency table is equal to the sum of f times xm over the sum of f. So let me just interpret what this means in plain English. When I use a table to help me figure certain calculations, this would imply that I take the sum. You can sit a little closer if you like. Yeah. You have the sum of column 4 divided by the sum of column 2. Right? That's informally what the formula states, is that when you have a frequency table, you're going to have to take the sum of column 4, whatever it is. I'll show you how we're going to get there. And then we divide it by the sum of column 2. So the frequency table that I give you already has the classes and its frequency. We need 2 more columns, so I just have to extend this. The 2 columns that we're going to be including are the are the xm values, then the f times xm values. We used this notation earlier. Anybody remember what xm stand for?
Midpoint?
Yes, that is your midpoint. So you take the midpoint of each class and then multiply it by the frequency to fill out the column 4. But of course, you need to get those midpoints. All right, so looking at our first class, Anybody remember what we did in order to compute the midpoint? What did I have to do again?
Add the lower and the upper and then divide by 2.
That's right. So I take 0 plus 3, divide that by 2. So 0 plus 3 is 3. 3 divided by 2 is equal to 1.5. Okay, what about the next class? What do you think your midpoint's going to be?
Nine.
Try again. We take 4 plus 7
5.5?
first.
Is it 4.5?
That's right. No,
I have
5.5.
5.5. Right? You do 4 plus 7 first, so that's 11. And then you divide by 2. So I think if you enter it in your calculators, be sure to put parentheses like how I have it around the 4 and 7. So like whatever I literally type, let me just erase this ending part. The way that I have it written, 4 plus 7 in parentheses, then divide by 2, that will give you your next class midpoint. So it should have been 5.5. Okay, what about the next class? From 8 to 11.
9.5.
Yeah, that's gonna be 8 plus 11 divided by 2, which is 9.5. Well, I'm gonna stop you guys there. Can you develop a pattern?
4.
It's going up by 4. And let's just look at 2 lower class limits. If I take the difference between 4 and 0, that is what?
4.
That is 4. Right, just checking it again. 16 minus 12 is 4. We get our class width. So now I can use this, after I did a couple examples of the midpoint, I'm just using this class width, namely the number 4, to fill out the rest of column 3. So 9.5 plus 4 is what?
13.5.
The next one?
17.
17.5?
0.5, yeah. 21.5.
And the last one?
24.5. Oh, 25.5.
There you go. It's okay. All right. Now, in the 4th column, you just take all the frequency values. You take the frequency of each class and multiply by the midpoint for that class. So, for example, you do 9 times 1.5, 9 times 5.5, 15 times 9.5, and so forth. So if you take 9 times 1.5, I think that's 13.5. Let me just double check.
Yeah.
Okay. 9 times 5.5 will be what? No, 9 times 5.5. Yes, 49.5. Then we do 15 times 9.5.
142.5.
142.5. Then we do 8 times 13.5.
108.
108. Then we do 8 times 17.5, 7 times 21.5. The last one I'm going to do, 1 times 25.5. That one's easy. It's 25.5. The other two, I got to use the calculator. 8 times 17.5 would give you 140. And then 7 times 21.5 is 150.5. Okay, so we have our table completed, majority of it, or all of it. Now I just gotta apply the formula. So the formula states that the mean of our frequency table is the sum of column 4 over the sum of column 2. So I just got to get these two values. Look at column 2. If I take the sum of the frequencies, that's essentially going to be now my bottom number. So you need to take 9 plus 9 plus 15 plus 8 plus 8 plus 7 plus 1. What would that be?
57.
57? Let's see. 18, 15 is 33, and 41, 49, 50. Yeah, 57. The bottom number is definitely going to be 57. So that goes on the bottom. What goes on the top is now the sum of column 4. So you take f times xm, and you add up all these values. So you do 13.5 plus 49.5, all the way down to the 25.5.
629.
You got 629?
Yeah.
Okay, let me just double check. What did you get again? 629, you said?
Yeah.
For some odd reason, I got something else, just slightly. Unless
I got
added both.
629.5.
629.5? I may have added wrong. I may have forgotten a decimal somewhere, or I added too many decimals. Let's see. I got 630.5. Let me just try it again.
$629.5.
Yeah, it's probably me. $629.5. My bad. So we take 629.5. That goes on the top. That's the sum of your column 4 over the sum of column 2, which was 57. So take the top number divided by the bottom number and then round. If you do round it to 1 decimal place, what do you get?
11.
Yes. Here's the tricky part with this one. If you write the number 11, unfortunately you're gonna get the problem wrong. You have to write 11.0. Right?
Okay.
Yes, because it says that you have to round it to 1 decimal place. So, well, if you're doing it on MyLab, that is. If you're doing this problem on MyLab and it says to round it to 1 decimal place, then you have to include that 0.0. Although the answer is 11, still the same thing. They wanted you to round it, so you have to show that there's this decimal. After the decimal point, there's a number there. That number is 0. Doesn't make sense, but that's the technicality of their coding for it. All right. Questions? By the way, I have my graphing calculator, right? So I'm just waving it so you guys can see it. I'm not going to teach you how to solve these problems in the graphing calculator. You definitely can, but if you have one, you definitely could use your graphing calculator like the TI-84 Plus or just a TI-84. The only thing is, I recommend that you watch a YouTube video because I more or less want to show you the formulas and talk about other things. So if your instructor, by the way, gives you a problem where there's going to be many data values, then yeah, calculator seems legit to use or learn to use. But if you have a small data set, then learning how to use the formula isn't that too bad at all, especially if you know how to set up your table.
What's the name of this type of problem?
This one is called finding the mean for a frequency distribution.
Thank you.
I'm just writing it out. For a frequency distribution or table. I think some textbooks, they'll just say table, frequency table. It's okay if we move on to problem 10.
Yeah.
All right, problem 10 states that we want to find now the range, sample standard deviation, and sample variance for the given data values below. And if necessary, round all final answers to the nearest 100th place. In other words, you're rounding it how many decimal places? 2, right? Rounding it to 2 decimal places. All right, so let's take care of the easiest one. The easiest thing here to find is your range. How do you compute the range?
The largest value subtracted by the minimum value.
Yeah, max minus min. Well, you only have 5 data values. Can you find the max, determine the max and min? Yeah, the max is 21. The minimum value, smallest one, was 11. So 21 minus 11 is
10.
10. So that's your range. Voila, you're done. Okay, so we need a couple of formulas now. We need to figure out what's the sample standard deviation, then figure out what's the, we first figure out in this order, the sample variance, then the sample standard deviation. So the sample variance is usually denoted by the letter S, or S raised to the second power. So S squared is equal to the sum of each data value minus the mean over n minus 1. What I should have technically wrote there on the top was the sum of each data value, the sum of the difference between each data value from the mean squared over n minus 1. When we look at this and using a table, this is just simply going to be the sum of column 3 over n minus 1. Then for your standard deviation, again, this is going to be for a sample. We use the letter S, and we say that it's equal to the square root of your sample variance. My bad. So it should be the square root of S squared, or simply the square root of the sum of the data value minus the mean squared over n minus 1. Now, remember, both sample variance formula and the standard deviation formula, they include two other notation there, x bar and n. We already know n represents the total number of data values, and x bar is your sample mean. So before I can go ahead and create a table, first figure out what the sample mean is. All right, so to get our sample mean, x bar, we, again, just got to take the sum of all the data values divided by n. So you take 11 plus 12 plus 14 plus 17 plus 21, you get some answer, and then divided by the total number of data values. So what number goes on the top?
$75.
75. What number goes on the bottom?
5.
5. So you take 75 divided by 5, and that gives us your sample mean.
So it's 15.
That's going to be 15. Okay, now create and complete.
Quick question. Where you got the 75?
You have to add up all the data values. So the data values were 11, 12, 14, 17, 21. Add them up, you will get 75. Sounds good? Hello?
Yes, yes, yes. Sorry.
Okay. So now we're going to create and complete the following table. So your first column, you list all your data values. They were 11, 12, 14, 17, 21. Then we're going to take the data value. We're going to deviate. We take the data, each data value subtracted from the mean. And then whatever we get, we're going to square those values. So we do 11 minus 15, 12 minus 15, 14 minus 15, 17 minus 15, and 21 minus 15. So what's 11 minus 15?
-4.
-4. 12 minus 15?
-3.
-3. 14 minus 15?
-1.
-1. 17 minus 15?
2.
2. And 21 minus 15? 6.
6.
There you go. So now we're going to square each one of these values that we got from column 2. We take -4 squared, -3 squared, -1 squared, 2 squared, and 6 squared. Now just be careful when you enter this in your calculators. Just remember that anytime you have a negative number and you square it, the result is always going to be what? It's going to be a what type of number? No. It has to be a positive. A negative number squared is always positive. Yes. So just be mindful of that. So when you want to compute -4 squared, it's the same thing as saying 4 squared. When you have these decimal representations, or whatever the case may be, if you want to show that's true in your calculator, with the negative numbers, make sure you put them in parentheses, like the way I have it presented on the screen. So -4 squared is the same thing as 4 squared. That's going to be 16. -3 squared, same thing as 3 squared, it's 9. -1 squared is the same as 1 squared, it's 1. 2 squared should be 4, and 6 squared is 36. So what we have to do in order to get our value of the variance, at least for the most part, is just to first get this sum. Add up all the values in column 3. So you take 16 plus 9 plus 1 plus 4 plus 36. That's going to add up to what?
$66.
66. Okay. So this allows us to find the variance because we have all the information. To find the variance, again, we say f squared was equal to the sum of the data values minus the mean squared over n minus 1. I know that the top number is now corresponding to the sum of column 3. If you just look back at what I wrote earlier. So we will get 66 on the top. N is your total number of data values, which is 5. And then you have to subtract 1 from it. So if n is equal to 5, then what's 5 minus 1? Yeah. 4. And then you now will take 66 divided by 4, and this gives you your variance. $16.5. Did I have to worry about rounding here?
To the hundredth?
well, we had to round it to 1 decimal place, but is there any to 2 decimal places? But technically, not speaking, what number is in the 2nd decimal place? There's a 0 there, so there's no, you don't need to do any rounding, right? This thing literally ends with a number in the 1st decimal place, so there's no rounding done. Your variance is 16.5. Okay, now you can find that. Now, lastly, you find the sample standard deviation. The way that this is obtained now is, well, we say S is equal to the square root of the variance. So since the variance is 66, you would need to take the square root of that value and then round it to 2 decimal places. If you do the rounding, approximately the square root of 66 is equal to what? The rounding, by the way, is 2 decimal places.
Is it 8.1?
You get around to 2 decimal places. So you got the first 2 numbers, 8.1, but what should come after this 1?
2.
A 2. Oh, my bad. So your solution is 8.12. And that's it. Any questions? Let me just rotate the screen so that way you get to see the whole thing. But any questions to problem 10?
No.
Sounds good?
Mm-hmm.
All right. So we're now going up to problem number 11, and I'm just gonna leave this for 1 more minute. Problem 11 is on the 5-number summary. So just like how I did problem 10 by hand, we're gonna do problem 11 by hand. But when you want to find the sample standard deviation, or I don't think it gives you variance. Variance, you actually have to do something manually. But the sample standard deviation, the 5-number summary, your calculator, depending if you have the TI 30X multi-view or a graphing calculator, you should be able to get the get those things with no problem. Again, sorry, Rachel. Yes. Where are we gonna go to get this? An email will be sent, and then you could, if you scroll all the way back up to in the chat, Raphael gave us a web link to our page. Oh wait, well, you're not gonna see this one for right now because we didn't. We're still recording. How about this? Well, here's the thing. I didn't realize the time here. I lost track of time. It's 12:17, which means that technically this review was supposed to be over at 12:30 today. So I know that some of you have online classes, or you have a next class or something. We do wish to continue this, but I do think we should take a break if we want to continue. I'm so sorry, I lost track of time. I should have went at a faster pace. How about I take a break and we resume around like 12:35?
All right.
Sounds good. We take a break.
Okay, thank you.
And then we'll do the second half. Okay.
Mhm.
So I'll just write it in the chat so that way you guys know.
12:30, 35.
12:35. Yeah.
Oh, thank you.
If you want, you guys can look at sorry, I was writing in the chat. Oops, meant to write wheel with the apostrophe. We'll resume at 12:35. Yeah, so pretty much I've covered today. I was ambitious because I tried to cover 4 chapters today. We did basically 2.5, 2 3/4. So when I come back, we'll finish up the rest. All right. That might take us up until like 2, and then you guys can enjoy the rest of your Saturday. So I'll be back. Yeah, but if you guys want, yeah, I'll leave the Zoom open. If you want, Raphael, if they want to like look back at any previous problem, you could just, if you want to, you could just slide it here. Let me just set the unlock though. My settings, because you might need the password. I gotta update this thing too. Okay, so problem number 11 states that we have to find the 5-number summary and construct a box plot for the temperatures in degrees Fahrenheit in 9 different cities on New Year's Day. So the 5-number summary, do anybody know what it consists of?
Is it the maximum, the minimum, and Q1, Q2, and Q3?
That's right. So I'm just going to put it in order. They are minimum, Q1, Q2, Q3, and the maximum. So Q1, Q2, and Q3 are your quartiles: lower quartile, the middle quartile, and the upper quartile. So here are the guidelines to get the 5-number summary. The guideline states the following. First, if necessary, have the numbers in order from lowest to highest. Step 2 is, well, from the 5-number summary, after you have the numbers in order, you should be able to determine the min and max. Then, after you determine the min and max, you determined your quartile 2, right? You figure out what's the value for quartile 2. And the way that we do this, when you want to find Q2, is going to be the median of the entire data set. All right, it's the halfway point of the entire data set. To find Q1, which is your lower quartile, you will need to find the median of the lower half. Once you find the median of the lower half, you can now proceed to finding Q3, which is finding the median of the upper half. Okay, so here goes. Look at your data values. Can we put them in order? What would be the first value?
10.
It'll be 10. The next value after 10?
20.
20. Then 34. 37. Say it again. 41. 46. 62. 68. 77 is the last one. Okay, so you can go ahead and find your min and max, right? The min would be what value?
10,
10. The maximum?
77.
77.
Mm-hmm. Okay, so we have our min and max. Now, if you want to find Q2, you would need to take the median of the entire data set, right? So how many data values do we have?
8,
Try again.
9.
There's a total of 9 data values. So when n is equal to 9, 9 is an odd number, the median of the entire data set is the middle value, right? So Q2 is equal to the middle value. And what is our middle value?
41.
41, right? So I'm just going to circle it. 41 is our Q2, 10 is the min, and 77 is the max. Okay, so now we got to find Q1 and Q3. By our guidelines, you need to take the median of the lower half. So how many values, by the way, are in the lower half?
5,
Try again.
4,
4.
sorry.
It's 4 because we're not including the value of Q2, right? Q2 is what separates the lower half from the upper half. So the median has to be from these sets of values, taking a median of 10, 20, 34, and 37. Well, since 4 is an even number, then the median must be equal to the sum of the two middle values divided by 2. So we're going to take 20 plus 34, divide that by 2. What's 20 plus 34?
54.
54. And then if you take 54 divided by 2, what do you get?
27.
27. All right, good. So Q1 is basically right here. It separates basically the bottom 25 from the upper 25. So Q1 was 27. Okay, now we got to do Q3, which, by the way, states that we have to take the median of the upper half. So how many values are in the upper half? It's still 4. You start with 46 and you go all the way up to the maximum. So it's 46, 62, 68, 77. You take the average of the two middle values, which is 62 and 68, and divide that by 2. So what's 62 plus 68?
130.
130. 130 divided by 2 is equal to
65.
65. So roughly speaking, these bars are what I'm used to basically write out where the location of Q1 and Q3 were. So if you actually want to write it out, the 5-number summary in order is going to be 10, excuse me, 10, 27, 41, 65, and then 77. Any questions?
No.
All right, now we got to do the box plot. So first I draw a line that represents our temperatures. And we got to give it a scale. So I'm going to start with 0. And just by looking at these numbers, we started with 10, we ended with 77. I'm going to go up by 10s, right? So we have 0, 10, 20, 30, 40, 50, 60, 70, and 80, right? 80 is where I can stop at technically because I know in this data set, the max was 77. All right, so now that I draw the number line, I do my scaling. You plot your 5-number summary. So the first number was 10. The next number was 27, which should be closer to 30 rather than 20. The next number was 41, so that's close to 40. Then 65 is in the middle of 60 and 70. And then 77 is closer to the 8. So I plot my 5 points. I draw a line that goes through, that starts with the min all the way to the max. Then I create a box from Q1 to Q3. And I draw a line, a vertical line that goes through Q2. So this would be your box plot for your data set. Each of the points that I have in blue represents a point, a value from the 5-number summary. Any questions? How did I put the line in the middle? Oh, that's just one of the rules. This states that you start with the minimum, and the line runs from the minimum all the way to the maximum. So I start with the min, which was 10, and the line has to end at the max. Oh, that's a vertical line that goes through the Q2. All right, the box is for Q1, Q3, but the Q2, the box, sorry, the vertical line goes through Q2. Yep. And that's it. That will be your solution to problem number 11. Hold on.
Can you
let me ask a
rotate it
question.
so we get the whole picture?
Sure. What happens with a larger number of data sets? That depends on what your professor wants you to do with that data set. So like, for example, if you have 20 data values, I think you can still do it. It's still practical. But when it starts going to like 30 data values, 40 data values, 50 data values, it gets tedious. And you may want to use a calculator that can do it for you. If you use a calculator, it gives you the 5-number summary, by the way. The same way like how you can use the calculator to compute the standard deviation of a data set, you can also use the calculator to get the same steps, essentially, to get the 5-number summary.
Can you bring it down just a little bit so I can see the question at the top?
Oh, sure. My bad.
Thank you.
You're welcome. Any other questions?
Yeah, I just asked that because our professor doesn't give us like 9 and 10 numbers. He gives us like 40 numbers.
Who's your professor?
Professor, I think Linton is his name.
Oh, okay. I think in his particular course, he asks you to learn how to use a particular calculator, such as like the graphing calculator, like the TI-84. Do you have one?
Yes, I have it.
I don't know the commands off my head directly, but there's a YouTube video that you can possibly watch with the steps, how to enter the values, all of them, into your calculator, and then how it spits out the 5-number summary.
Okay, thank you.
You're welcome. Anybody else? Okay, let's just continue. Problem number 12, I have to rotate it back because I'll need the space when it's horizontally. In problem 12, it states a weight of 220 pounds among a population having a mean weight of 165 pounds and a standard deviation of 24.9 pounds, right? Use the range rule of thumb to identify the limits separating, the limits separate values that are significantly low or significantly high, then determine if the given value of 200 pounds is significantly low, high, or neither. So here's just a couple of notation, and then I'll clarify the range rule of thumb. So because we're dealing with the population this time, when we look at the mean and the standard deviation, we use the Greek letters because we have a population. So the Greek letter for the mean looks like a U. It's called mu. So this represents the population's mean. On the other hand, for the standard deviation, we use something called little sigma. It looks like you're drawing a cherry. So this is your population's standard deviation. Okay, now let me just clarify the range rule of thumb. So the range rule of thumb tells us that essentially 95% of the data values are going to be within a range of 2 standard deviations below the mean or 2 standard deviations above the mean. So here's a number line that helps you to clarify range rule of thumb. Let's say somewhere around here in the center is your mean. Then if I know the location of this particular points that I'm circling, these dots, those points are the values that are either 2 standard deviations below the mean. So you take your mean minus 2 times whatever the standard deviation is. And then you do the same thing on the other end, the mean plus 2 times the standard deviation. So 95% of the values are within this particular range, and we say that they are not significant. Anything now that's to the left of the mean minus 2 standard deviations, we call that significantly low, right? So anything in this particular area is significantly low. And anything in this particular region is significantly high. This is essentially what you have for the range rule of thumb. The range rule of thumb is also allows us to estimate a standard deviation if we don't have one, but we're not using that particular formula. We're looking at this picture. Okay, so we've got to first determine those 2 limits. The lower limit, which is just trying to figure out what's this value, and figure out the mean plus 2 times the standard deviation. The way that you figure it out is, well, you know what the mean is. The mean was 165, and your standard deviation was 24.9. So you just have to replace, just make substitutions and do the calculations, right? So mean was 165, standard deviation was 24.9. So for your 2 limits, the mean minus 2 times the standard deviation, this is just 165 minus 2 times 24.9. And then we do it again for the other limit where we just add. So what's 165 minus 2 times 24.9?
Is it 115.2?
Yep, it's 115.2. So that would have been this value here. And let's look at the other one. What's 165 plus 2 times 24.9?
$214.8.
214.8. So that value goes there. So those are your 2. That answers the first question. Identify the limit separating the lower, the significantly low or significantly high values. Well, it's going to be the range of 115.2 to 214.8. Okay, Now we answer the last part of the question. The last part of the question states, determine if the given weight of 220 pounds is significantly low, high, or neither. So technically speaking, on my number line, where would the 220 be located?
It'll be past the 214.
Yeah, it should be above, it should be to the right of 214.8. So if x is equal to 220 and it's to the right of one of our limits, then is this value going to be significantly high, low, or neither?
High.
High.
High. Yep. So let's just write it out. So since x equals 220 is not in the range of 115.2 to 214.8, and it's to the right.
I'm sorry, can you repeat how you got the 220?
Oh, 220 was given.
Oh, okay, I got it.
Yep. And since that value, the 220 is to the right of 214.8, we say 220 pounds is significantly high. And we're done. If I had a value like 200, 200 would have been not significant because it would have been somewhere in that where that blue box is located, where it says not significant. And if I had a number that's less than 115.2, then those values are significantly low. Can you speak louder? This guy do it by hand, but it's just really honestly computing two values, and then you make a comparison. Where is the next value, the data value? Where is it located on that line? Is it in the range or is it outside of the range? If it's to the left of the lower limit, then it's significantly low. If it's to the right of the upper limit, significantly high. Any questions with problem 12? Okay, let's look at problem 13. Problem number 13 is another application where we involve the mean and the standard deviation. But look at these keywords, by the way. In this problem, it stated that we had to use the range rule of thumb for problem 12. Problem number 13 is going to say something else, right? It states that at one college, GPAs are normally distributed, and we know what the shape of that is, with a mean of 3 and a standard deviation of 0.35. Using the empirical rule, you want to approximate the following percentages. Students having a GPA of 2.65 and 3.35, having a GPA between 2.3 and 3.7. Okay, now when we think about normally distributed data sets, what type of shape will that data set look like? A normal. It looks like a bell. That's right. And when you're dealing with the empirical rule, there's legit only 3 answers that we can get, especially if you're looking at a range that is exactly 1, 2, or 3 standard deviations below or above the mean. The empirical rule is summarized as these approximate percentages: 68, 95, 99.7. So let's draw a bell. Okay, sorry, I need a little bit more room there. So let's say down here. Okay, this is good enough. So my bell shapes never come out nicely. Sorry about my bell. Yes. Timmy, you'll be able to watch these when we post it. My bad. I was trying to fix my belt. All right. Not the best with bell. So at the peak of your bell shape, you have your mean. So I'll write it out as you can use sample, or this works for both sample and population. I'm just using the population notation now, so that way you can get a little bit more familiar when you see it down the road. So again, the empirical rule tells us about the percentages of values that can fall within 1 standard deviation, 2 standard deviations, or 3 standard deviations away from the mean. Right? So if we're 1 standard deviation away from the mean, we're at these particular values. We say the mean minus 1 standard deviation, or the mean plus 1 standard deviation. On the other hand, let's say, again, these are not the best pictures, so my illustration is a tad off, but nonetheless, we'll be able to solve this problem. So the next one would have been the mean minus two standard deviations, or the mean plus 2 standard deviations. And the last one, let's say down here, is the mean minus 3 standard deviation, or the mean plus 3 standard deviations. So now let's fill this table in. We know that the mean was equal to 3, right? So mean was equal to 3. The standard deviation was 0.35. So let's just say that I continually subtract 0.35 from our mean. Then those values that I have on the left, we're basically going to fill them in, right? For example, what's 3 minus 3.5? Anyone? What would the, if you take 3 minus 0.35, what do you get?
2.65.
Say again?
2.65.
Yeah, 2.65. Okay, good. Now, continually subtract 0.35. What would be the value in purple? This one. Want to help me out? What's continually subtract 0.35?
235.
2 point what?
3.
2.3. And if I subtract another multiple of 0.35, what would the last value here be?
195.
1.95.
Yeah.
So 1.95 indicates that we're 3 standard deviations below the mean. 2.3 indicates that we're 2 standard deviations below the mean. And 2.65 indicates that we're 1 standard deviation below the mean. Okay, now we're going to do it in the opposite end. If you look at the first one to the right of the mean, that's the mean plus 1 standard deviation. That means that I take the mean and I add 0.3 or 0.35. So what's 3 plus 0.35?
3.35.
Mm-hmm. What would the next value be?
3.7.
3.7. And the last?
0.05.
4.05. 4.05. Okay, so the empirical rule now is how we answer this question. If you're in that range, which is shown in red, from this region here, that means that you're either one standard deviation below or above the mean. So for those particular data values, by the empirical rule, that's 68%. The ones that are in purple, namely the 2.3 all the way to 3.7, 95% of the data values falls in that range. And the one in pink is where we say that, okay, 97.5% of those values will be 3 standard deviations below or above the mean. So we use these 3 percentages to answer the question. Part A states approximately what percentage of students have a GPA between 2.65 and 3.35. So if you look at our bell shape that we drew, that range 2.65 and 3.35 is that 1, 2, or 3 standard deviations within the mean.
One.
Yeah, it's just 1 standard deviation within the mean. So this would have tell us that, okay, the final answer here should be what percentage?
68.
Yeah, that's it, 68%. That's all you had to do. Look at the next one. It says between, what percentage of students have a GPA between 2.3 and 3.7? So how many standard deviations are you within the mean?
2.
2. This is 2 standard deviations within the mean. So what percentage will that be based off of the empirical rule?
95%.
95%. That's it. That's your solution. All you had to do was, because the fact that it's a normally distributed data set and it gives you the mean and it gives you the standard deviation, create the bell shape and then use the 3 percentages. The answer must be 68, 95, or 99.7. As long as it's within exactly 1, 2, or 3 standard deviations within the mean. Now, if I were to do something like, let's say between 1.9 and 2.3, there's a more precise percentage that we have to compute. That's just, Hillary, that's just the 68, 95, 99.7 is just another way of calling the empirical rule. It's only those 3 percentages. Timmy, I see you also raised your hand. What question do you have?
What's up, Anthony? I had the same question. I was just unsure as to like where those 3 percentages come from.
Oh yeah, those 3 percentages are just from the rule. Yep, I think if you look at your, oh wait, no, you're in Professor Lackik's class, right? I don't know what page it is in the stats in the stats 2 book, but it should be somewhere in chapter 2 if you have that book. Do you have it with you? Yeah, that one. It should be in chapter 2 somewhere, so you can see exactly a better picture than mine's. All right. Any other questions to problem 13?
No.
Oh, Alexandra got one more last question. Yes, it would always be those 3 percentages. As long as the data, the range that we're looking at is either 1, 2, or 3 exact standard deviations within the mean. If I had something like 2.65 to 3 or 2.3 to 4.05, then it becomes complicated. That's where we're going to learn about other techniques in chapter 6. Okay, let's look at problem 14. So problem 14 is where we wrap up chapter 3. So it states that a body temperature of 97.4 degrees Fahrenheit, given that human body temperatures have a mean of 98.20 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Find the corresponding z-score for the body temperature, and then determine if the score is significantly low or significantly high or neither. Essentially, there's this standard z-score, and the way that you solve this problem is you use the formula, and then from that formula you apply the range rule of thumb basically again all over again. So the formula for z, our z-score or standard score, is saying that z is equal to the data value minus the mean over the standard deviation. I didn't write this one in any notation, only because of the fact that the way that we're going to compute z-scores is the same, whether you have a sample or population. Just got to remember, data value first, minus the mean, divided by standard deviation. So looking at our problem here, what is the data value?
97.4.
Yeah, 97.4. What is the mean?
98.20.
Yeah, 98.2. And our standard deviation?
0.62.
0.62. Just inserted everything now into the formula, right? You're taking all these values and you insert it into the formula. So what you're going to get is that z is equal to 97.4 minus the mean of 98.2 over 0.62. So you work out the number on the top first, 97.4 minus 98.2. You would get something like negative 0.8. And you have to divide that now by 0.62. So you take your answer divided by 0.62, you get a decimal number. With z-scores, just remember that when you're computing them, you have to round it always. If rounding is needed, round it to 2 decimal places. So what is the value of z that we get here?
Negative 1.29.
Negative 1.29. Okay. So look at this z value, and that will be the z-score now for 97.4 degrees Fahrenheit body temperature. What we want to do now is determine if this is significantly low, high, or neither. So when you look at, instead of it in terms of x, rather the data value, when you look at it in terms of z, the 0 is what corresponds to a mean. The -2 and the +2 are what separates the significantly low and significantly high values. So where would the -1.29 be located? Would it be located to the left of -2? Is it located somewhere in the middle of -2 and 2? Or is it located to the right of 2?
To the right of -2.
Say it again, Alexandra.
To the right of -2.
Yeah, it should be to the right of -2. And in particular, it should be somewhere between the -2 and 0. So somewhere around here. Let's say here. This is z equals -1.29. Okay, now because it falls within the range of -2 to 2, we can say that it's not significant, right? So since z equals -1.29 is between z equals -2 and z equals +2, then this value this body temperature, the z-score, whatever, then this is not significant. If it was something like a number greater than 2, like 2.5, that would have been significantly high. A significantly low value would have been something like negative 2.5, right? So just doing like a couple examples. If this was negative 2.5, we would have said that's significantly, I'm just gonna abbreviate it, low. And if I had like 2.5, that value is significantly high. This is just like the range rule of thumb problem, with the exception that instead of looking at it in terms of X, in terms of the original data values, you're looking at it in terms of Z. Z's, you're standardizing all the data values, right, essentially, for your data set. So it's like a double dip with that problem of the range rule of thumb. Any questions? Okay, let's do a little bit of probability now. So I've done chapters 1 through 3 with us so far. The remaining 6 problems was on probability. When I do my next workshop, whenever that is, I got to work out the dates with Raphael. I will include probability again. So like these problems that I'm doing, some of them you will see, but I'll cut it down. I'll trim it down some. Okay, so this is just the very basic for probability. It states which of the following values cannot be a probability. So let's see here. What do we know about probability values? It's a numerical measurement that's between what 2 values?
Zero and 1.
0, 1.
0 and 1, right? So let me just write it out. So the probability of A occurring is where A is an event, by the way, or some event, is always within this range of 0 to 1, where we include 0 and 1. So which one of these values are not going to be probabilities?
Negative 0.06.
Yeah, that's one of them. What else?
Yes, square root of 3.
Yeah, square root of 3, because that's bigger than 1. Say again?
1.73.
Yeah, 1.73. Any others?
1.29%.
Be careful. 1.29% is actually a probability. Here's how I can tell. You see, 1.29%, you can actually write this out as a decimal number. You divide it by 100, right? 1.29% is the same thing as saying 1.29 divided by 100. And if you divide this by 100, you get 0.0129. So that would be between 0 and 1. So it is a probability.
Okay. It's 8/3.
8/3. That's right. The other one has to be 8/3. The ones that I circled here cannot be probabilities because it does not fall in our range. And we're done. Okay. The only emphasis on this is because when I work with fractions sometime, or sometimes we have to do a computation, students will mistakenly say a fraction that's greater than 1, or they will say a negative number where they don't mean it, but it's a way to correct yourself, okay? To know that this is all a red flag. I did something wrong with my computation. All right, we can move on. Let's look at problem 16 now. Problem 16 states that the probability that Lewis passes his statistics exam is 75.4%. State the complement and find its value. Okay, so usually in statistics, we use letters or to talk about an event, or we summarize that letter with a little phrase. But let's just say we let A be that Lewis passes his exam. Right? A is our event, and it means that Lewis passes the exam. What is the complement of A?
1.
Say it again.
The number 1.
No, not the number 1.
No?
No. We're going to use the number 1 for the formula, but I have to first state this in words. Anybody know what it means for two events to be complements of each other? Now, again, this depends on if you've covered probability in your class or not. But if you covered probability, you should know what complement means.
I thought that the complement was always going to be number 1.
No, the complement is not always the number 1.
Okay.
But we use the number 1 in a formula. Anybody know what the complement is?
The
Or
complement
at least have seen that word in class?
35.6.
No, I don't want the value. I want you to, here's the thing. I can just give you the formula, say how to compute it, done. But you need to first state it in words. Okay?
1
So
minus.
no. I don't want the numbers in words. I mean, I want the event in words. You got to tell me what the complement is. If A is that Lewis passes the exam, then by the definition of a complement,
Oh, it means that he may not pass the exam.
yes, exactly. Complement
The
is
opposite.
saying, yeah, right. It's like saying the opposite. So we use this notation A bar to mean not A. So if A is that Lewis passes the exam, then not A means that Lewis fails the exam, right? If you're not passing it, then you're gonna fail, right? So A bar is Lewis fails his exam. So now we want to figure out its value, right? Find the value of A bar. And we use a formula. The formula states that the probability of A, whatever event it is, plus the probability of A bar is always equal to 1. So that's why, Alexandra, when you were saying 1, you're not wrong. Because when you take A,
No.
the probability of A, and you add it to the probability of A bar, or the complement of A, those two probabilities are 1. But because the fact that we want to find the probability of A bar, then I just got to subtract the probability of A from 1. Here's the only thing though. When you're starting to work with probability problems, if the likeliness of an event is given as a percentage, for calculation purposes, you use the decimal representation, right? So in this problem, it's stated that the probability of Lewis passing the exam, since A represents him passing, was 75.4%. But you need to write that out first as a decimal. So what's 75.4% as a decimal number?
0.754.
0.754. Okay. So if you want to compute the probability that he fails the exam, then this is now going to be equal to 1 minus the probability of him passing, which as a decimal was 0.754. So 1 minus 0.754, that would have been the 0.246 that you've mentioned. And as a percentage, that would have been 24.6. I think on my lab, they might just say leave it as a decimal. But if you want the the significance of that number, it implies that as a percentage, his chances, the likeliness that he'll fail is 24.6%. Questions? Right, so just remember, complement means the opposite. So if we have A, then A bar means not A. Sounds good?
Yes.
Okay, let's continue with more probability. So in problem number 17 now, we're looking at a two-way table. A two-way table is used when
I'm sorry, can you
essentially.
show problem 16 again so I could screenshot it?
Sure, I'm sorry. Let me know when you get it.
I got it. Thank you so much.
You're welcome. So problem 17 now is a two-way table. Sometimes the entire complete two-way table is given to you. Sometimes it's not, and you have to fill certain things in, namely your totals. The reason why we call it a two-way table is because essentially the data values can be separated as two different variables. Like, for example, the table describes the smoking habits of a group that suffers from asthma. So that particular group of people that suffers from asthma, you can separate them by gender, male or female, or man and woman. And then you can also separate them based on their smoking habits, whether they're non-smokers, whether they do some occasional smoking, whether they do some regular smoking, or they do some heavy smoking where they say, oh, I'm going for fresh air outside. But nonetheless, those are your two variables, their smoking habits versus gender. All right, so before we can answer any probability question, first thing is to complete the table if all the totals are not given, right? If you have the table where you're just given, basically, let's see, can I draw on this? Can I write? No, you won't be able to see it clearly. But if I'm basically given everything up to the first three columns, sorry, the first 5 columns and the first 3 rows, then that last row and last column, you have to fill it out. And it's not that hard. For example, let's look at the non-smokers. Non-smokers were separated based on man or woman. So if you take the sum of those numbers, 373 and 418, you get the number of people that are non-smokers. So how many non-smokers were there?
791.
791.
791. How many occasional smokers do you have?
100.
100.
100. How many regular?
156.
156. And how many heavy smokers?
72.
72. Okay. Now for men, you would add up everything in the rows. So you go from 373 all the way to 80. Oops. No, sorry, you go all the way up to 33. So if you add those 4 numbers, what do you get?
536.
536. And now you do the same thing for women. So it's 418 plus 50 plus 76 plus 39. That would be what?
583.
That's right. So we get 583. In this very last box that I'm putting a big circle around, oval, that's your sample space. The one that so far currently doesn't have any value. And the way that we get the sample space, you got to be very careful here. Because we have 2 different variables, the smoking habit versus gender, you either take the sum of the genders or you take the sum of the smoking habits. If you take the sum of the gender, 536 plus 583, that tells you how many people there are. And that would be 1,119. On the other hand, all right, so I got it by just adding these 2 values. On the other hand, if you were to add up the last row, 791 all the way to 72, that would have told you the number of people with smoking habits. So 791 plus 100 plus 156 plus 72, even if you give it a shot, add it up, that turns out to also be 119, right? So you just got to include the 119 once. Do not add everything. Just either add the row once, the last row, or add the last column to get your sample space. Does that sound good? Okay. Now
Yeah.
we can go ahead and answer the probability question. And just keep in mind that in the blue font, it says our rounding rules. So part A states, the person is a male. Well, how many men do we have in this table?
536.
536. So if one person selected at random, it's the number of ways to select a man. So it's 536 different ways out of the total number of people, your sample space. So your sample space is 1,119. And if you want to read it out now as put it all together, the probability of selecting that the person is a male or a man is 536 over 1,119. Now, on my lab, you would have to, of course, maybe simplify this, namely like writing it out as a decimal approximation. So in your calculator, it looks something like this: 0.478, 9, 9, nines, and so forth. So we look at the value in the fifth decimal place, that 9. It tells the 9 that comes before it to go up by 1. But technically speaking, when you think about rounding 9 up, what comes after 9?
1.
Well, careful. What comes after a 9?
10.
A 10. So to show that we're rounding this up, that 9 to a 10, we replace this 9 with a 0 and we add 1 to the 8. So this will be approximately 0.4790, right? So for this 8, you just add 1. Makes sense, by the way. You know, if we have 0.4789 and we're rounding it up, then the next number should be 0.4790. That's part A. For part B, it states find the probability that the person is a regular smoker. So how many different ways can we select a regular smoker based on our table?
$156.
156, and you divide it by your total, your sample space. So 156 over 1,119. And again, we're going to have to take this value, round it to 4 decimal places. If you do this correctly in your calculator, you get 0.1394. Okay, and then there's a part C. Part C states that the person is a woman and an occasional smoker. By the way, before I begin solving part C, how many people are we selecting at random here? No, for this last part, yeah. Unfortunately, it's not 2. If you go back at the very beginning,
1.
It says that if it's one person selected at random. So just keep in mind that we're looking at one particular event, but for this one event, we're looking at this one trial where we're selecting this one person. The person has these 2 characteristics. It's a woman and an occasional smoker. So there's a way to do the end when you have to select one person at random, right? So let me just write out the notation. Probability of woman and occasional. Look at our table again. In our table, I can highlight the row for a woman. There it is. I can also highlight the row for occasional smokers. Now, sorry. I'll do it this way. That's our row. So we have the row for the woman, the occasional smokers was down the column. Look at my highlights in yellow and green there. Do we have anything in common? Do you see any intersection?
50.
Yeah, that 50. Wherever you have an intersection, That's what it tells you, that the two variables share something in common. So how many women were also occasional smokers? There were 50 of them. So it's 50 divided by, but be careful now, you divide by our sample space. Right? We're still dividing by the sample space. So it's 50 over the 1,119. So if you do 50 divided by 119, this is going to be approximately 0.0447. And that's your solution. So parts A through C.
Excuse me, the numbers, the C, why not the woman, total woman 583 divide 50 divided by 583. I always think it's 50.
No, because I'm going to get there in problem 18. Don't worry, I get there in problem 18 to clarify. By the way, for problem C, part C, the key term here was the word and. Okay, one person was selected. We're dealing with an and case, so it's where they have to share something, some characteristics. The part that you're thinking about is conditional probability, which I'm going to do next. But I just want to have the screen out like this for right now. But if you don't have any, if you guys don't have any questions, I can move on.
No, thank you.
Okay. So I'm going to rotate this back, but before I rotate it back, I actually really need the numbers. So we have 791. So same data set. 100. 156, 72, 538, 583, and then 1,119. Okay, so now let's look at problem number 18. This is where it gets a little trickier. So here it states the table below describes the smoking habits again of the same group that suffers from asthma. There's three parts. Parts A, B, and C states that, okay, well, if one person is selected at random, just one, find the probability that the person's a male given he is a heavy smoker. Part B, the person is a heavy smoker given the person is a male. Part C is the person is an occasional smoker given the person is a woman. In problem 18, parts A, B, and C all share one key word. What's that one key word?
Given.
The word given. That's right. So when you see this word given, it implies conditional probability. So I just want to give you a little bit of notes, a little bit of notation. When we have conditional probability, the notation for it is the probability of B given, so that bar means given, A. The probability of B occurring given A occurs. So in plain English, right, that notation, probability of B given A means the probability of event B occurring given that event A already occurred. You see, I wish for this lesson, when I teach conditional probability, I wish I have a guest speaker. I wish I had Cardi B coming in for this one. No lie, no joke. Because when you look at occurring versus occurred, one of them is past tense, one of them is future tense or present tense, right? So which one is the past tense?
A.
When you look, say it again.
A.
A, yes. So when you look at occurred, that's going to be your past tense. So that tells us that event A is the first event. The occurring is future, present, or future tense. So that tells us that event B is our second event. Okay, so we're computing the probability of the second event, given that the first event already went by, already occurred. So the formula for this, by the way, I never use it. I mean, you can, but you do it intuitively. It says that the probability of B given A is equal to the probability of A and B, whatever they have in common, divided by the probability of A. But again, I don't use this formula detailed. I do it intuitively. I know that the chances or the likeliness of A occurring, that bottom number where you have the probability of A, it's basically the number of ways that the first event can happen. And then for the top number, it's whatever they have, the two events have in common. So let's look at part A. Part A stated that the person is a male given he is a heavy smoker. So looking at our notation here and knowing what's first event versus second event, is the male the first event or the second event? The part where it says the person is a male, is that the first event or second event?
The second.
It's the second event. So for notation purposes, we're computing the probability of male given that the person is a heavy smoker. So when I solve this problem intuitively, I look for the number of ways, the total number of ways of selecting someone that's a heavy smoker. And then out of that many heavy smokers, how many of them are males will go on the top, right? So let's look at our table. How many heavy smokers we have?
72.
There were 72 heavy smokers. Out of the 72 heavy smokers, how many of them were men?
33.
33. So we have 72 over 33 over 72, right? The 72 in words, that's the number of ways of selecting someone that's a heavy smoker. And on the top, you have a heavy smoker that is a man. Sorry for my chicken scratch writing. Okay. And of course, you do the computation in your calculator. You take 33, divided by the 72, and then round to 4 decimal places. You would have got approximately 0.4583. And that's it. That would have been the solution to part A. Part B states that the person was a heavy smoker. Sorry, the person is a heavy smoker given that the person is a male. So although part A and B look almost identical in terms of the events, their probabilities are not, because of the fact of the way that the events are positioned around the word given. This time, heavy smoker, is it going to be the first event or the second event? Can't be the first event. It's the second event. It's going to be the event B. That's right. So this time in part B, we will start with heavy smoker, right? compute the probability of getting selecting someone that's a heavy smoker, given that the person is a male. So intuitively, when you look at your table, find the number of ways of selecting a male. How many males are there?
538.
538. Out of the 538, how many of them were heavy smokers? 33. So this time we get 33 over 558. Oh, wait, no, 538. And then you round your final answer. So you will say 33 divided by 538 is equal to 0.0613. And then there's a part C. So part C states the person is an occasional smoker and the person's a woman. So occasional smoker, is that event A or event B? Looking at our notation. Event B, and person is a woman is event A. So just use your notation. We're gonna have for part C, the person, probability that the person is a, what was it again? Occasional smoker, given that the person is a woman. So let's look back at the table. How many women were there in this data set?
583.
583. How many of them now were occasional smokers?
50.
So it's 50 over 583. And then you round this off to 4 decimal places, and you get 0.0858 approximately. So I'm just going to rotate back my screen because I gave you a lot of information there. Use part A as like our guide, and just keep practicing different examples. Like for this, you can do so many. There's like so many possibilities, because for the smoking habits, there were like 4 choices. For gender, there's 2. So 4 times 2 is 8. And then you have to keep playing around with it. I think I did 3. I think you guys could probably do the other 5 as practice. Just to practice it, you know? Questions? So we've seen that when one person is being selected and we have the word and, it's an intersection, whatever the 2 events have in common. When we have the word given, it's stronger because now we have to do a conditional probability, right? There was a condition, an underlining condition regarding the second event. That condition was that the first event occurred. And now there's one more word we have to focus on when we're dealing with one person selected at random. Here it states that, I'm doing the same table again. The person's a man or a regular smoker. The person is a non-smoker or heavy smoker. What's the key word in parts A and B of problem 19?
Or.
The word or. That's right. Anybody know what probability rule is associated to the word or?
Addition.
Addition, that's right. So or is associated to addition. And we have the following probability rules. We say the probability of A or B is equal to the probability of A plus the probability of B, minus the probability of A and B. Sometimes when you have or, the or cases, you have to subtract off whatever they have in common at the end, because of the fact that you're trying to, what's the term? You're trying to avoid double counting or double dipping, namely double counting. Okay, so let me just refill my table again. So I think this number was, crap, I always forgot that first one, 791. I was too lazy to add it up. 100, 156, 72, this was 1,119, that was 583, and this was 538. Okay, So let's look at part A. Part A, we're dealing with the person is a man or regular smoker. So I'm just going to write the word regular. So by our formula, just by using some substitution here, man is the first event, regular is the second event. That's our A and B. So it's the probability of man plus the probability of regular smokers minus the probability of them both, right? Meaning essentially the probability of getting a man that is a regular smoker. Okay, so we computed these probabilities earlier, no? The probability of selecting a man is 538 out of 1,119. The probability of getting a regular smoker is 156 out of 1,119. And again, if you want those numbers, look back at problem 17, parts A and B. But this time, if you want the probability of both, how many men were regular smokers? 80. So it's going to be 80 out of the 1,119. So you add, because we have the denominator is the same, you just leave it alone. You just add or subtract the top. So you take 538 plus 156 minus 80. That should have turned out to be 614. And when you divide that by 1,119, that's approximately 0.5487. Done. Okay, let's look at part B. Part B states that the person is a non-smoker or heavy smoker. So we do the probability of non-smoker or heavy. This is equal to the probability of getting a non-smoker plus the probability of getting a heavy smoker minus the probability of both. So, how many non-smokers were there? So as a probability, we say 791 over 1,119 plus the probability of getting a heavy smoker, which is what?
72.
72. So you gotta write it out as a probability. So you say 72 over 1,119 minus any intersection. Sorry. So if you look at your two events, we had heavy smokers and we had non-smokers. Is there any intersection between those two events?
No.
No, there's no intersection. So technically speaking, the probability of both is going to be equal to what number? If there's no intersection, then the probability of both is technically equal to what? Or yeah, it's 0. If there's no intersection, it can never happen. So if it's never gonna happen or occur, never ever, then it's 0. So you just gotta worry about the two other numbers. So it's 791 plus 72 over 1,119. So 791 plus 72 turns out to be 863. And if you divide that by, again, that 1,119, then round to 4 decimal places, you get 0.7712. Just I'm gonna spend one more minute on this. So there's a difference between why the part A and part B. If they have some sort of intersection, we call them not mutually exclusive. In other words, not mutually exclusive implies overlap. An overlap, whatever they have in common. In this example, in part B, it's mutually exclusive because they're disjointed. They don't share any outcomes in common, right? So that's just a couple of extra terminology. All right, that's problem 19. Let's do problem 20, and that would wrap up the show. I'm just giving it a minute, so that way if you want a picture, you can take your picture, no problem. But we did a very thorough review today. Proud of ourselves.
Thank you for that.
You're welcome. Problem number 20 is when you have the at least case, and it's also being combined. So it combines a couple of multiplication rules. It combines, sorry, a couple of rules. It combines a multiplication rule with the complement rule. So it states that it is reported that 68% of high school graduates in New York State goes directly to college. I don't remember what year I pulled that up. I was doing this, and this is a final exam question at another college I used to teach at. I don't teach there anymore, but I pulled this question up from there. If 4 graduates were randomly selected, what is the probability that in part A, none of the 4 high school graduate goes directly to college, and then part B states at least 1 goes to college? All right, so I'm just going to rotate my screen because I will need a little bit more space than what's shown. So first of all, when we're dealing with computational problems that involve percentages, be sure you rewrite the percentage as a decimal. So what is 68% as a decimal? Say it again?
0.68.
Oh, yes, 0.68. All right, so if we want to get the probability, so 0.68 would have meant the probability of A, right? I'll write it this way. The probability of one person, one graduate rather, goes to college. Okay. In part A, we want to figure out the probability that none of the 4 people, right? We have 4 graduates being selected this time, not just 1, 4 graduates, that none of the 4 that we select went to college. So if the probability of 1 graduate goes to college is 0.68, what do you think will be the probability that the graduate does not go to college? Yes, Hillary, it has to be 0.32, right? This is essentially the complement rules being applied. It was 1 minus the probability of A, which is equal to the probability of A bar. 1 minus 0.68 is your 0.32. Okay, so if this question just stated that if 1 person was graduating, if we selected 1 graduate, then the probability would have been 0.32. But that's not the case. We're selecting 4 graduates. So we apply the multiplication rule. For part A, the probability that none of the 4 is going to be equal to the 0.32 times itself 4 times. Or we say 0.32 raised to the 4th power, right? Each 0.32 that you see there means that, okay, that's the probability that the first person didn't go to college. The 0.32 again means that the probability that the second person doesn't go to college. The probability that the third, and then lastly the 4th, right? So I could have underlined the values so you can see it. That's 1, that would have been my second person, third person, and 4th person. All right, so if you compute it in any way that you want, 0.32 to the 4th or 0.32 times itself 4 times, you would get, when you round it to 3 decimal places, you get 0.010. And that's it, done. for part B, if you want to do the probability of the at least one goes to college, then this is equal to, this is where you apply another formula. It's a complement rule. It's the 1 minus probability of none of the 4. Right? It's 1 minus 0.010, which is 0.99. So let me just explain how I did part B. So how many people did I select in this example, by the way? It was 4, right? So let me just do this demonstration with 4, but it doesn't always have to be 4. It could have been 5, 6, how many people you wanted. But nonetheless, if you do the exactly cases, like exactly 1 person, exactly 2 person, or exactly nobody, right? If you take the sum of all these probabilities from 0 to 4, that sum is always equal to what number? Do anybody know? It's always equal to 1. It's always equal to 1. And if you're dealing with the at least one case, at least 1 would have been 1 or more, right? So at least 1 equals 1 or more, or exactly 1 or more. So just doing a little substitution here, rewrite. We have that the probability of getting it 0 times plus the probability of at least 1 is equal to 1. But this comes from now the fact that you can use the complement rule. If you want to compute the probability of at least 1, then just subtract the probability of 0, that it never happened, on both sides, and you get this newly used formula. Probability of at least 1 is equal to 1 minus the probability of 0, which is technically 1 minus the probability of not A. And that's it. So I think that's it for my review. Yeah. Anybody have any questions regarding this one? I know I kind of rushed through it, but let me know if you have any questions.
No,
Thank you for your time.
Alrighty, everyone. So the recording will be available shortly. We gotta probably give us a few hours on that. It's just that this file is gonna be an extremely large file. So when we have it uploaded, we'll definitely send an email to everyone. Okay. Thank you all for attending the meeting. For those that attended via Zoom, don't worry about attendance. The attendance we get it automatically through Zoom. So we'll have that, and we have how long you've been in the meeting. All right. Thank you all. I hope you find this workshop, this review session successful, and we should definitely run some more in the future.
Very helpful. Thank you so much.
You're welcome.
Thank you.
Have a good one.
Thank you so much. Thank you. Have a good day.
You too. Have a good day. We'll stop the recording now. Stop recording.